Fog, a word that evokes a sense of mystery, a blanket of white that softens the edges of the world. It transforms familiar landscapes into scenes of ethereal beauty, shrouding everything in an air of secrecy. But fog is more than just a visual spectacle. It plays a crucial role in our planet's climate and ecosystems. Imagine yourself walking through a dense forest, the air thick with moisture. The sunlight struggles to penetrate the canopy, casting an eerie glow on the forest floor. As you venture deeper, the trees seem to disappear into the mist, their outlines blurring into the white void. This is the magic of fog, a phenomenon that has captivated poets and scientists alike for centuries. Fog, in its essence, is simply a cloud that touches the ground. It forms when the air near the surface cools to its dew point, the temperature at which it can no longer hold all of its water vapor. This excess moisture then condenses into tiny water droplets, suspended in the air and creating the familiar hazy effect we call fog. But the formation of fog is a delicate dance between temperature, humidity, and air movement. Different types of fog, such as advection fog and radiation fog, arise from specific atmospheric conditions, adding to the complexity and intrigue of this natural phenomenon. The birth of fog begins with the air's capacity to hold water vapor. Warm air acts like an invisible sponge, holding more moisture than cold air. Picture a warm summer day. The air feels heavy and humid. As the sun sets and temperatures drop, the air cools, and its capacity to hold moisture decreases. This cooling process is crucial for fog formation. As the air cools towards its dew point, the invisible water vapor in the air begins to condense. Imagine tiny water molecules like dancers in a crowded room, bumping into each other as the air cools. When they bump with enough force, they cling together, forming larger and larger droplets. Different types of fog form under different circumstances. Advection fog, for instance, occurs when warm, moist air moves horizontally over a cooler surface like a cold ocean current. Picture a warm breeze blowing across a cold ocean. The contact between the warm air and the cold water chills the air, causing the moisture to condense into fog. Radiation fog, on the other hand, typically forms on clear, calm nights when the ground loses heat rapidly through radiation. Imagine a clear night sky with no clouds to trap the heat. The ground cools down quickly, cooling the air near the surface and causing fog to form. Fog may seem like a simple phenomenon, but its composition is surprisingly complex. While primarily composed of tiny water droplets, fog can also contain ice crystals, especially at lower temperatures. These ice crystals can create different types of fog, such as freezing fog, which can coat surfaces with a layer of ice. But fog's composition goes beyond just water. It acts like a giant air filter, trapping pollutants and particulate matter from the atmosphere. Imagine fog as a giant net catching tiny particles of dust, smoke, and even pollutants from cars and factories. While this trapping effect can have negative consequences, such as reducing air quality, it also plays a role in scavenging pollutants from the atmosphere. Fog droplets can collect and remove these pollutants from the air, eventually depositing them back onto the Earth's surface through precipitation. This scavenging effect is particularly important in urban areas, where fog can help to mitigate the effects of air pollution. However, it's a double-edged sword, as the trapped pollutants can also have detrimental effects on human health and the environment. Section 4. A Tale of Two Planets, Fog on Earth and Beyond. Fog, while a common sight on Earth, is not unique to our planet. Other planets and moons in our solar system also experience fog, albeit with some intriguing differences. Take Titan, Saturn's largest moon, for example. Instead of water, Titan's fog is composed of methane and ethane, hydrocarbons, that exist as liquids at Titan's frigid temperatures. Mars, our red neighbor, also experiences fog, but it's much thinner and less frequent than on Earth. Martian fog is thought to be composed of both water ice and carbon dioxide ice, and it plays a role in the planet's water cycle, albeit a very limited one. Venus, our scorching hot sister planet, experiences a different kind of fog, one composed of sulfuric acid droplets. This dense, toxic fog shrouds the planet's surface, making it impossible to see from space and creating a hostile environment for life as we know it. These examples highlight the diversity of fog in our solar system and the different roles it plays in shaping planetary climates and environments. Studying fog on other planets not only provides insights into their atmospheric processes, but also helps us better understand our own planet's climate system. Section 5. Conclusion. Mysteries yet to unfold. Fog, the silent enchantress, continues to fascinate and intrigue us. From its ethereal beauty to its crucial role in Earth's climate and the intriguing fogs found on other planets, this atmospheric phenomenon holds many secrets yet to be unveiled. We've explored the science behind fog formation, delved into its complex composition, and journeyed to other planets to witness their own unique fogs. Yet there's still much we don't know. How does fog interact with different types of pollution? What role does it play in the global water cycle? And how do fogs on other planets compare to those on Earth? These questions and many more continue to drive scientific inquiry, urging us to further explore and understand the mysteries of fog. As we delve deeper into the science of fog, we gain a greater appreciation for its complexity and its vital role in shaping our planet and beyond. So the next time you find yourself enveloped in the embrace of fog, take a moment to appreciate the intricate dance of nature unfolding before your eyes.